So it's good to see faces of friends, faces or names of friends, and also to see some others who are not in my acquaintanceship, but perhaps it will be after this. Some of the people in this meeting today, we met last week in Ghent, where we had this ADA Europe yearly conference, and perhaps this event here might have been a very interesting addition to that conference, but never mind. We'll speak about that in the future if it happens. So allow me, or in fact, you allowed the title. The title is one of those strange things that I like to say and to mention. And I'll start with the disclaimer. And disclaimer is that I do not believe in teaching languages, regardless of what the language is. This has to do with my old age, perhaps, and the education I received. I believe that languages, whatever they are, be they Greek, Latin, Ada, Spark, others, are there to point to concept, to address concept, but you have to learn the concept before the technicality of a language. That's what I believe, but of course languages are necessary in informatics. And what I'm going to tell you here is sharing a little bit of the nice moments in one of the recurring lecturing that I give. And the topic of that is concurrency. And I hope to be able, throughout the talk I'll be giving here, to persuade you that the title and the abstract that are on the workshop page are true. They're speaking the truth as opposed to telling lies. I believe that the starting point of this presentation should be easy for you to share. I would be surprised if you disagreed. Disagreeing on the, rather, I would expect you to agree to the fact that concurrency per se is a difficult concept. And one of the reasons it is difficult, in my interpretation of it, is that to understand concurrency, to think of concurrency, I think you have an idea of an architecture, where by architecture I mean the parts and their collaboration, the way entities relate to one another, for what purpose. And concurrency, in the way I would describe it, if I were to describe it to the outside public, I would say that it is there to help create or give a shape to a collaboration among parts, which is helping to deliver a functional purpose. So it's a collaboration in which you assign tasks, not in the ADA sense, but you assign activities to parts in order that each part can do a special job that can be more easily traceable, that can be more easily maintained. All of those, principles that I should not really expand on because you should be familiar with. The point I'm trying to make here is that at the top, concurrency is a difficult concept. And at the bottom, I'm saying that my observation looking at fourth-year students, higher education university students, is that they are, on average, very little equipped at seeing these patterns of collaboration. So although they have programmed, and they have programmed for 4 years at least, and perhaps more based on their educational career before university, but they don't quite see concurrency. They see perhaps what programming languages can offer them, if they've seen any concurrent programming language, but very little they see about concurrency as a concept and into patterns of collaboration. And if I were to say, adults really know better often, and which is another difficult thing in life. Second premise in what I want to say today is the way I interpret my role as an instructor. Perhaps it's an illusion, I don't know, or a delusion, if you like, is to try and facilitate dawning of ideas into people's mind. Is not. I really refrain. I find it very frustrating, very dissatisfactory when students relate to me by way of obedience. You are the instructor, I tell you what you want me to say, and this must be all. So that is terrible. I find it terrible, horrendous. And instead, I'm fighting my way, I'm helping, and sometimes I succeed, and when it happens, I rejoice in helping them understand. And it doesn't have to be a synchronous moment. It's not that they have to understand in class. They may understand the week after by reflecting back on something. But the point is that that moment, the dawning, that epiphany in the etymological sense, is of extreme value, super, super, super valuable. And one of the consequences of an epiphany in concurrency is that you start becoming familiar with architecture, software architectures, in the sense of, collaboration of parts. And that, when that happens, and luckily, as I said, happens, is a very beautiful moment. And there are tricks, or at least I believe I've found a couple of moments in which this happens more easily. More into personal beliefs, so you allow me to express myself into what I believe in the regard of the topic of the discussion. When it comes to concurrency, the concepts I believe are foundational are tasks in the Ada sense and asynchronous communication. Why for tasks? For two reasons, fundamentally. One is because they are there to stay. Because tasks are heavyweight entities, it would be completely stupid, allow me to say this, silly, say, and wasteful to have tasks come and go for doing very little. So because they are heavyweight, they have an import on the software architecture. So that leans very well with the notion of think of your architecture, what you're there for. So this is reason number one. And reason number two is that tasks are what they say they are, a unit of computation. And I like when a unit of computation declares itself as such, and not a magical procedure that if I'm passed as a parameter, I become the body of a task. So that is the one thing I believe in. The other is I believe in asynchronous communication, so collaboration in an asynchronous manner. And the reason why I believe in asynchronous communication is that I find it to scale naturally, therefore well, into distribution. And because distribution is another essential dimension of nowadays programming, it is important that the way of thinking architecturally as a way of thinking across. It's not that you make assumptions on the one end, which are going to break when you go distributed. Second thing in this premises, and I'm coming nearly to the end of premises, so again, bear with me on this one, is that I dislike personally, therefore refrain from programming models that impose architecture, In a sense, I'm also staying away from programming models that are, do it yourself. I have no opinion, says the language, do me with anything. But at the other end, I dislike programming models that impose, you have to use me like this, because if you don't use me like this, nothing happens, or things don't happen the way you would want. An example in question is the actor model. The actor model is a very nice solution for certain problems, but it really forces a solution. And I don't think that's appropriate for the teaching purposes that I have. Another thing I like a lot when we talk about concurrency is that I would like programming to be ecological. That is to say, not to be wasteful, not to need very many lines of code to tell what you need to say. In other words, I prefer to see higher level abstractions as units, as opposed to a little bit of dots that when you join the dots, they give shape to Donald Duck or something. And this is easy to measure by a student. So you can, in a sense, the analogy that I'm often using in this one, I don't expect to share it, but you agree with me on this one, but if you do, that's all the merrier, is that I really like to show them programs which do very significantly complicated things in a few lines of code, but tell exactly what you want to do In a sense, it's like, the application part is the tip of the iceberg, and the runtime underneath is the really the bulky part, except that the bottom part of the iceberg is doing what you want. And it is not, the one against which the Titanic collapses. So I call this, with a bit of creativity, if you like, ecology of programming. I like, as I said, using solutions that require very few statements, but do something very specific, very precise, and semantically rich. Okay, and I'll try to give you a specific example, which I'm calling the peak of beauty. Not because I teach it, but because it's a nice experience. End of my premises. Ada comes into the picture very well, because it has I believe Ada has a splendid model of concurrency. Splendid. It is very insightful. It's a product of very intelligent reflection. And it is so cool and so nice that you can work on it embedded as well. You have it in your program, and you take it on straight on to the hardware, no operating system in the middle, if you like, because it is what it has to be, which is very nice. Into this model of concurrency, the tools that I like to use are tasks, protect the objects, entry queues, and the beautiful, very intelligent, very clever eggshell model, which other languages have completely blundered. And those are useful instruments into the peak of beauty, if you like. I don't know, many of you are novice to Ada, so you don't know what the object is. So most of you, I suppose, are very familiar with it, so I will not spend more than a few seconds on this. So that's a very simple and not particularly novel example of a protected object. In fact, it's a type in which the value of this is showing that there is an interface exposed which says I'm having two entries. Now, regardless of the name of the thing, the value of what these entries are and the fact that they express a condition for which the statement after the begin may occur is a very powerful concept in situations that are normally, in fact, I can say, are very apparent to students. Students, when they are pointed to see them, they see them, say, oh, yes, indeed, that's what it is to say. So basic ingredient, tasks, protected objects, entry queues, and the way the eggshell model tells what happens when you are using any of these entities. So this is an egg. It's a boiled egg, sectioned. And this is exactly the slide I'm using a student at some point, more than halfway through lecture series I give them on concurrency, 4th year. What is interesting in this analogy of the eggshell model is that there is a center where you want to be, which in other sort of lecture topics is called critical section. It's a private part, if you like, that is exposed, it is shared to multiple users. And you want to have guarantees that when you are on the inside of a critical section, you have exclusive rights if you make modification to the thing. So that's easy for people, for students to understand. So, oh, yes, I want to have guarantees that I can touch private parts that are shared in an exclusive manner. That's very good. So second thing that they do understand is the shell part. Shell in the sense that you are outside of the thing, and when you're outside of the thing, you have to request access to it. Say, I need to use this. May I do it? This is also easy for them to understand. So there must be a mechanism, which is of course syntactically mostly, so that you say, there is this thing, which when I invoke it, allows me to have exclusive access to it. And of course, it is understood that I cannot get access to it if others are having it. So there is a waiting as part of the story, okay? What is most interesting to students, and it is not obvious at all, is that this is not enough. That in seriously, serious, more than seriously, serious programming, you not only you want to have exclusive access to a private part that you share with others to do your things, or to do your things collaboratively, of course, but also it is important that when you get exclusive access to that private part, the private part is in a functional state useful to your doing, because it is completely pointless to get access to something in an exclusive manner and you don't find it useful to your purposes, because the functional state the thing it is in, it is not appropriate. This is why this example I was skipping over before is very explanatory. A buffer is useful to those who write when it is not full. A buffer is useful to those who read from it when it is not empty. So these are obvious conditions. It is very silly to give exclusive access to a writer if a buffer is full. It is equally silly to give exclusive access to a buffer for reading when the buffer is empty. Okay? So I think this is a very natural concept, but the way to handle it is not evident. And Ada has a beautiful solution to this. Again, Ada in the sense, Ada has seen the problem and provided a beautiful solution to it, more than Ada has invented a beautiful solution to something and then called it a problem. Okay? So that is the part that becomes very attractive, the fact that you want to do something, for example, write into a buffer, and to do this, you need exclusive access, but maybe the buffer, the moment you ask for it, is full, and it is pointless when you are allowed exclusive access into it. So the dilemma here, which Ada solved very well with the so-called eggshell model, is that you ask, may I write? And the resource says, oh, I'm sorry, man, you cannot write because I'm full. But I keep you within the shell so that you don't have to compete with others that are outside of the shell and may cause starvation on you. So that is very interesting. So in the mental model of students, when they understand exclusive access, they have this notion inside, outside. And if they happen to come from the Java view of the world, poor them, because they have a notion, which is completely bogus, that there is a single queue outside where everyone that needs to enter in an exclusive manner are going to wait, which is super messy. Not as the Argentinian player, but you understand what I mean, It is completely confused. So there has to be a queue on a condition attached to the service you want to get. And the service is, of course, exclusive. And the condition allows you to be queued, waiting for that condition to be satisfied in a place that does not compete with those who are outside of it. So you retain some degree of privileges. So that is super cool. And when does it come into a very visible situation that needs this? Is the resource allocation problem. That's not really the peak of beauty. I'm coming to a peak of beauty in a moment, but the resource allocation problem is a very explanatory situation in which Ada's eggshell model is phenomenally good. as long as the problem is specified as I'm saying now. The key point, I think you can read for yourself this example that describes what this general, if you like, resource allocation problem is. The key point is that you want to guarantee requesters that when they request service, and the call that they make returns only when the request is satisfied, and it will be satisfied. So that is a super interesting condition, if you like, super interesting element of a specification. It's not like, when I was a kid and I was living at a seaside beach village, and there was only a single telephone box in the village, and of course, people were queuing for the telephone box, And I, that was a kid, had no patience to stay in the line, and therefore I went to the beach and come back. And when I went to the beach and come back, I lost my position in the queue. So you see what I'm trying to get at, The notion that you ask for a service and you cannot get service now, in a silly model, in a naive model of concurrency, would force you out, and then you try in again, and you enter the queue again. And when you leave the queue and enter the queue again, the best that can happen to you is starvation. And starvation is never a good thing. So it's important to pass on, this in this particular specification, the notion that it's a feature, it's a very desirable feature that requesters place their request, and their requests are satisfied eventually. And there is no return until satisfied. So you place a request, you stay there, and there are means to say how long you'll be there, based on the problem you have, based on the number of concurrent clients that are there and all of that. So that is super nice because it's not obvious. And the consequences are very visible. Starvation is a very visible thing. When you think of this in a more general sense, you find that synchronization on access to resource has fundamentally 6 different dimensions. Okay? That's not my invention. This is something which is taught by lecturers in concurrency. So I will not be spending time on this. Again, you may read through this, and then there are also recordings, so you may come back in case this is interesting to you. But what I'm driving to is that the features or the dimensions of this synchronization problem grow increasingly more complex. And the complexity culminates when the synchronization succeeds, meaning exclusive access to the resource you ask for, succeeds based on the parameters of your request. That's what makes it extremely subtle and complicated. So in the resource allocation problem, we make this promise: request will be satisfied, that is, there will be no return that is not satisfied. But then the question comes, look, but how can you service me without knowing how many items I want from this pool, for example? Will my request have a bearing, have an influence of the serviceability of it? I'm asking for 3, but only 2 are available. Oh gosh, what happens? Maybe the person behind me, the requester behind me, only asks for 1. Should they not get it ahead of me? And what do I lose if people pass by and I'm falling behind? So this dimension number 6 is extremely problematic, and it's a very intellectually challenging problem for students and for instructors, in fact. So let me stay in this, of course, I think it's easy for you, I suppose, to understand the drive of this observation. This calls for requeues. Requeues come in exactly for this type of problem. So let us contrast 2 solutions, 2 situations, you see, in which you have the serviceability, the success of your request is contingent on your request parameter. Okay, you have a simple case in which every request has only one, a cardinality of one. I'm requesting one item in a pool. Okay, so in that case, there's no problem. Requests are indistinguishable. FIFO queuing is perfect. There's no problem. Okay. Now imagine that you're extending Ada in this funny and not desirable manner, in which we're expressing a guard condition based on an input parameter. Let this example stay in front of you for a few seconds. So imagine that you have to have a situation in which you're managing a pool of resources, and clients may ask for any of them, any number, from 1 to all of them. And you have a problem of meeting the requirements I mentioned earlier. The requirement is this, that requests are satisfied. Requests are satisfied. So that is to say, the caller is not return control unless the service has been delivered. Okay. So the question I'm posing to students, I'm not posing it to you because they're all adults and experts, but is, okay, would this be a solution? The one in which a guard is using an input parameter of a call. At the end of the day, this would mean what I think is easy to understand, that the guard would open when your request would be satisfiable. And this is not a solution. Well, it is not a solution for a reason that has to do with the way Ada understands entry queues, which is a very plausible choice, in fact, to understand them. And is that the queue associated with an entry in a present object as a single condition attached to all the calls. Whereas this guard expression would differentiate each call in the queue based on its own specific condition. Can you see what I'm trying to say? And this would be a total abuse of the abstraction that Ada is offering. So you are trying, if there was the syntax, if this significance was allowed, you would have a situation in which the cost would be excessive and the benefit very little, because of course you would have the runtime semantics that the language is offering in implementing entry queues completely devastated by a naive use of what this would be. But the problem would stay. The problem would be that how can I meet this requirement? How can I meet this requirement? Is this requirement important? And the answer is yes, it is. It is for multiple reasons, and one of the reasons why it is that the service policy should not be visible to the client. The client is requesting for a service and should get the service delivered. Should not be part of, oh no, I'm sorry, I cannot give it to you, try it again. That is not a good service. So the requeue helps a lot in that notion. It's a very interesting solution to addressing this complex problem in a manner that stays consistent with the notion and with the runtime semantics of an entry queue in Ada, and consistent with the eggshell model, which I touched on earlier. Understanding what a requeue is also not obvious to students, and it is interesting. So, I mean, I understand that this is not a good pedagogical manner to start with a negation of this is not that. And that's why I added the premise to requeue is not. But requeues are best understood in examples and not in a statement in which you declare what they are as a notion, okay? So now we come to the peak of beauty. So bear with me on this. What is this peak of beauty? This peak of beauty is a problem which every time I schedule it in class, it's a beautiful experience because it is material for a flipped classroom. It's a moment in which it's students to work together, discussing, and the instructor is only the scribe, taking note of what the students think, what the student come up with, and discuss overall. This exercise, I find it especially useful and productive when it is collective. It is not people going off and say, I programmed it at home and this is my solution. It's a creative moment of thinking, trying to express your own meaning, trying to give a shape to the problem and give a shape to a possible solution. So what's the problem is not invented by myself. This is something that other instructors more famous than I am used in their own lecture series, and I found it particularly compelling, and I took it on myself, and I found it very useful and very satisfactory. So it's you're representing, of course, you can scale it so much larger, a circular line service with a single train. So there is a single train going along a circular line, and along the circular line there are stations that are used by commuters. So commuters come into the station from home or from work, stay at the station to board the single train that comes along the circular line, board the train, and get off at the destination station, be that for work or be that for home. And then after doing their duty cycle at home or at work, they go back. So that's a specification of a problem. It's fairly easy to understand as a concept. The train obviously has a finite capacity. To make it more interesting, there is no pre-booking, contrary to life experience, but students don't really pre-book their own trains, they are in the category of poor, and therefore they don't pre-book stuff. So it has a very obvious, immediate transfer to reality. So we understand what the problem is about. But of course, the challenge is how to map it into a concurrency model, because what they have in the reality, they are immersed into it. They don't see the architecture of it. They don't see the protocol of it. Sometimes, especially in Southern European countries, they don't even understand protocols in the sense, in the obvious sense of the term. So that's a problem that is given. And there are some interesting, very interesting intellectual challenges that come along with this problem. And are problems of architecture, that is to say, what are commuters, the train, the station, in terms of, the model of concurrency that we discussed? Are they all tasks? Now, of course, you'll have your own opinion about, your own intuition about it, but the answer is not, they are not. And there are very strong reasons why they are not. And it is very interesting to come to see those reasons. This is part of the epiphany that I meant. Second, interesting, at least to me, hopefully it is to you listening to this, intellectual challenge is, how does the journey happen? I had students who imagine that a commuter would be a task that would be enqueued in a task that would be a train. And therefore they thought that, and some of them continue thinking of that today, that the commuter task should be aware of the station at which the train would stop to decide whether to stay on or get off. Which of course is nonsensical, because that would completely violate the rule I mentioned earlier, that service is delivered according to a given service model without the client participating actively into the service being rendered. And can I provide a solution? Can I write in code a solution ecologically? Something which takes very little lines, very few lines of code, very few statements, but does it all in a semantically sound way. For example, one of the most obvious things you want to do is that you want to guarantee that getting off a train always precedes the boarding of it, which is not trivial. And of course, students living in Italy will tell me, but this never happens in reality, you know? How can you imagine that, you know, we let people get off a train before we board it? We always want to board it regardless, which is an evident violation of protocol. And of course, how can we guarantee that capacity is never exceeded as part of it? So that is what I'm calling the peak of beauty. Why it is a peak of beauty? Because in the time of this particular lecture, which is normally a couple of hours, it's always a very intense discussion in which the protagonists are the students, and the instructor is only there to steer a little bit, you know, to avoid that, you know, fantasy goes off and horrible situations, architecturally horrible, occur. That, you know, big problems are addressed, understood. If they are too difficult to solve on that lecture, then there is a spillover lecture to continue discussing. So that is super, super exciting, super satisfactory. And
Tullio, this is Jessie. I'm just going to give you a quick 5-minute warning.
Thank you very much. And I'm coming to the end. You see that I was just checking time that I would be coming to it. Thank you, Jessie. If you want to take a look at the solution, you snatch a picture, you know, take a photograph of this, and you download this code and you try it for yourself, and you'll find that it is cool. This is a rather complex system, semantically complicated, achieved in a very small number of statements. You have hardwired students who say, I want to do it in other languages because I find them better or because of other reasons. And for example, Google's Go gets very close to this, and it produces, in Go, it's possible to produce very nice solutions, not as nice as the one that I believe I'm sharing through that link, but it is more costly, it's less ecological. So that's an interesting challenge that I'm posing to students that are more fighting in the sense of, you know, I have something else to think or something. So that's the take-home message here. I will not be speaking it because you can read it for yourself. Some of these are pretty obvious. And one of the key insights I'm having out of this reflection and out of this experience is that Ada is cool in this regard, is because it's a language in which what you say is what you get. What you say is what you get, and it's important when you want to, you know, give shape to your architecture and get something done. And with this, I think I'm closing.
So do we have any questions for Tullio? We still have a few more minutes.
I have one, if I may. So I suspect, maybe I'm wrong, that you're using a requeue statement in your solution. And I wonder, so requeue is not allowed in the strictest profiles of Ada for concurrency that are called the Ravenscar and Jorvik now.
Mm-hmm.
So how do you approach these issues of having the right level of concurrence primitives with students, and how would you then justify that this or that level of concurrency has been supported?
Yeah, you know, I consider myself one of the co-inventors of a Ravenscar profile. So it's like, you know, I'm parent to it in a way, or if I'm not a parent, I'm an uncle or something. So I believe in it very much, but I would not classify it as a first thing in concurrency. Ravenscar being a subset, is being a restricted profile, is a way you understand by taking things off. So this peak of beauty problem that I described in this presentation would not fit a Ravenscar restriction, more than one, in fact, in particular, and that's fine with me, because at first you see that you have problems that are complex and you have a nice solution, and then you find in a totally different lecture, in a totally different topic, which is in fact real-time systems, you understand that you have overarching reasons to constrain the solution. And when you constrain the solution, certain things you cannot have, and therefore you renounce them. So this is the intellectual trajectory that I think I go. I would find it unnatural in this one to start from by prohibiting certain features as opposed to adding them.
So you were able to approach this issue of finding the right amount of concurrency primitives with the students, and they also have this kind of epiphanies that you described.
When I said these epiphanies, they do have. It's not 100% phenomenon, but it's beautiful. It's one of the one of the few things left that I like in my job. Is that you can see in their faces, these epiphanies, like, oh, I see it. And when they do, it's beautiful.
Okay, so we have just a couple minutes left before the break. If anyone has a final question, and if not, we can.
I have just a follow-up question. Unless Christophe has one. You first, Christophe.
Okay, thanks for the presentation. It was very interesting. I know it's another.
Speak the truth, Christophe. Speak the truth. Don't be political.
So I know it's an other workshop, but when you're speaking about teaching concepts for concurrency, what do you think of higher level language like TLA plus or things like that?
I believe that anyone would do, in the sense that I'm not like anything is fine. I'm saying that you have to have a problem that requires concurrency to be addressed. And then you choose what is also closest to your own sentiment. And then you sort of elaborate on that one. So that what I want to refrain from being the advocate of a language, because students tend to say, oh, well, this instructor is using that one, therefore I have to do it. And that's not passion. That's just obedience, which is really the opposite of what you need. So to me, the central thing is the concept you want to convey, which must be an abstract problem, but they can see, not something which is completely bogus or something. And then the way you want to give it a syntax fundamentally can be anyone, okay? And high level is better than low level, because if I have to go through that VSC, I would never come to anything sound, okay? Whereas if I started from something which is philosophical as opposed to programming, I'm getting so close to it. But the essential is that they can root it into something that they can view with their eyes, not the syntax, but the problem that is in front of them. That is so very important and so very helpful.
Okay, thanks.